1. Intergranular corrosion. Intergranular corrosion occurs along the grain boundaries of an alloy. It's common in stainless steels and aluminum alloys. Causes. It typically happens due to the depletion of protective elements like chromium in the grain boundary areas during improper heat treatment. Detection. This can be detected using techniques like microstructural analysis or electrochemical methods that reveal the weakened grain boundaries. 2. Galvanic corrosion. Galvanic corrosion arises when two different metals are in electrical contact in the presence of an electrolyte. Causes. When metals with different electrochemical potentials are connected, the more anodic metal corrodes faster than it would alone. Detection. You can detect galvanic corrosion by visual inspection, looking for signs of corrosion at the junction of the two metals, or using electrochemical measurements to assess potential differences. 3. Exfoliation corrosion. Exfoliation corrosion is a severe form of intergranular corrosion, where layers of the metal peel away. Causes. This type is often found in rolled products like sheets or extrusions, and is caused by the expansion of corrosion products along grain boundaries. Detection. It's usually detected through visual inspection for flaking or delamination, often confirmed by ultrasonic testing. 4. Oxidation. Oxidation is the reaction of a metal with oxygen to form an oxide layer. Causes. All metals, except noble metals, oxidize to some extent. The rate depends on the metal and environmental conditions. Detection. You can detect oxidation through visual inspection, looking for discoloration or oxide layers, and using weight gain measurements after exposure to oxidizing conditions. 5. Fretting corrosion. Fretting corrosion occurs at the contact areas between materials under load and subject to minute relative motion. Causes. This happens due to repeated cyclical rubbing between surfaces, leading to material wear and oxidation. Detection. Fretting corrosion is detected by examining the contact areas for pitting, discoloration, or material debris, often using magnification or surface analysis techniques. 6th, uniform corrosion. Uniform corrosion is the most common type of corrosion. It can be defined as the attack of the entire metal surface exposed to the corrosive environment, resulting in uniform loss of metal from the exposed surface. Causes. In natural environment, oxygen is the primary cause of uniform corrosion of steels and other metals and alloys. Detection. Uniform corrosion can be recognized by several visual and physical characteristics, including even surface degradation. The most noticeable characteristic of uniform corrosion is the even loss of material thickness across the entire surface of the metal. 7th, filiform corrosion. Filiform corrosion is a form of corrosion specific to painted steel, aluminum, and magnesium surfaces. It results in a detachment of the coating from its metallic support, which is caused by the surface corrosion of the underlying metal at the metal coating interface. Causes. This type of corrosion typically occurs on coated surfaces, when moisture or a corrosive solution penetrates through the defective coatings. It is caused by active galvanic cells across the metal surface. Detection. Filiform corrosion occurs under a thin layer of coating in the form of thread-like filaments. Filiform corrosion appeared on metallic surfaces that are covered with an organic film. Based on the unique appearance of fine filament lines, the pattern of the corrosion can be characterized. 8th, Pitting corrosion is a localized form of corrosion by which cavities or holes are produced in the material. Pitting is considered to be more dangerous than uniform corrosion damage because it is more difficult to detect, predict, and design against. Causes: the presence of aggressive chemical environments, such as chloride ions, which can penetrate the passive film on the metal surface and initiate corrosion at localized sites. Additionally, variations in the composition or structure of the metal, such as impurities or alloying elements, can create regions of increased susceptibility to pitting. Mechanical factors, such as scratches, crevices, or surface defects, can also act as initiation sites for pitting corrosion by disrupting the protective oxide layer on the metal surface. Detection: since spotting pitting corrosion with the naked eye is close to impossible, there are reliable ways to test for it. Testing can prevent pitting from wreaking havoc, so we recommend testing susceptible materials often. Common testing methods for pitting corrosion include: the first one is visual inspection. Using a microscope, a professional will count the number of pits in a given area. This helps them determine their size and distribution as well as the intensity. Second, sonics testing. Ultrasonic sound energy is transmitted through a coupling onto the metal. These ultrasonic pulses bounce off the metal and are converted into electrical signals. These signals will show the location of pits and other imperfections in the metal. And lastly, electromagnetic testing. Testing method is used to locate irregularities in the surface of conductive metals like steel and iron. Ninth, stress corrosion. This form of corrosion is particularly dangerous because it may not occur under a particular set of conditions until there is an applied stress. Cause: stress corrosion occurs when a material exists in a relatively inert environment but corrodes due to an applied stress. The stress may be externally applied or residual. Detection: a popular technique for identifying stress corrosion is visual inspection, in which specialists search for telltale indicators like visible damage on the material's surface, crack propagation, and initiation sites. This can be reinforced by employing methods like dye-penetrant testing, in which a surface is treated with a dye, and the dye's penetration reveals any cracks. 10th, concentration cell corrosion, a common form of localized corrosion that occurs when there are differences in the concentration of corrosive agents, such as oxygen, along the surface of a metal. Cause: concentration cell corrosion occurs when two or more areas of a metal surface are in contact with different concentrations of the same solution. Detection: detecting concentration cell corrosion involves a combination of visual inspection, electrochemical testing, and monitoring of environmental factors. For visual inspection, they look for areas of surface irregularities, including small pits or cracks, which may signify the presence of anodic and cathodic sites. Electrochemical testing techniques such as electrochemical noise analysis or polarization resistance measurements can provide quantitative data on corrosion rates and reveal the presence of concentration cells. And monitoring environmental factors such as oxygen concentration and temperature can aid in detecting conditions conducive to concentration cell corrosion. In the world of aviation, safety is paramount. Every aspect of aircraft operation is meticulously managed to ensure the safety of passengers and crew. One critical aspect that often goes unseen but is of utmost importance is corrosion protection control. Corrosion, the gradual deterioration of metal due to environmental factors, can compromise the structural integrity of aircraft if left unchecked. That's why corrosion protection control is integrated into every facet of aviation operations. Here are the key strategies employed in corrosion protection control in aviation. 1. Material selection. Aircraft manufacturers carefully choose corrosion-resistant materials like aluminum alloys, titanium, and composites for critical components. 2. Protective coatings. Specialized coatings are applied to aircraft surfaces to create a barrier against corrosion, with primers and top coats engineered to withstand harsh environmental conditions. 3. Routine inspections. Skilled technicians conduct regular inspections using visual checks and advanced non-destructive testing techniques to detect corrosion early. 4. Preventive maintenance. Preventive maintenance procedures, including cleaning, applying corrosion inhibitors, and repairing damaged coatings, are performed to minimize corrosion risks. 5. Environmental control. Hangars equipped with climate control systems maintain optimal conditions to reduce the risk of corrosion when aircraft are not in use. 6. Corrosion prevention programs. Aviation operators implement comprehensive programs outlining procedures and best practices for managing corrosion risks. 7. Data monitoring and analysis. Corrosion data is continuously monitored and analyzed to track corrosion rates, identify trends, and refine maintenance strategies. 8. Regulatory compliance. Compliance with aviation regulations and guidelines set by authorities like the FAA ensures the highest standards of corrosion protection control. By implementing rigorous corrosion protection control measures, the aviation industry safeguards the safety, reliability, and longevity of aircraft, ensuring passengers can travel with peace of mind. Aircraft corrosion and treatment methods. Let's explore the different types of corrosion and their respective treatments. Surface corrosion. Treatment. 1. Inspection. Regular inspections are crucial. This involves visual checks and the use of tools like borescopes. 2. Cleaning. Remove any contaminants like dirt, oil, and old paint using solvents and detergents. 3. Mechanical removal. Use abrasives such as sandpaper or power tools like grinders to remove the corrosion products. 4. Chemical treatment. Apply chemical rust removers or pickling solutions to dissolve remaining oxides. 5. Neutralization. Rinse with water or a neutralizing solution to halt the chemical reaction. Pitting corrosion description. Treatment. 1. Detection. Use non-destructive testing. NDT methods such as ultrasonic testing to detect pits. 2. Mechanical cleaning. Employ fine abrasive pads or brushes to clean the affected area. 3. Chemical cleaning. Use a mild acid solution to clean the pits thoroughly. 4. Filling. For deeper pits, apply a filler material compatible with the aircraft's metal. 5. Sealing. Seal the area with a corrosion-resistant primer and topcoat. 3. Intergranular corrosion treatment. 1. Identification. Utilize NDT methods like eddy current testing to locate affected areas. 2. Surface preparation. Clean the surface using solvents and abrasive techniques. 3. Heat treatment. Reheat the affected parts in a controlled environment to restore the metal's integrity. 4. Replacement. In severe cases, replace the affected component entirely. 5. Protective coating. Apply a protective coating to prevent future occurrences. Galvanic corrosion treatment. 1. Inspection. Identify areas where different metals are in contact. 2. Isolation. Use insulating materials like rubber or plastic washers to separate the metals. 3. Cathodic protection. Apply a sacrificial anode to protect the more reactive metal. 4. Coating. Ensure both metals are coated with a protective barrier. By understanding the types of corrosion and implementing appropriate treatments, the aviation industry can maintain aircraft safety and performance, ensuring they remain airworthy for as long as possible. So, why is corrosion protection and control so important? Corrosion protection and control are crucial for several reasons. First and foremost, safety. Corrosion can compromise the structural integrity of aircraft, leading to potential failures. Secondly, longevity. Proper corrosion control measures extend the lifespan of aircraft components, ensuring they remain in service longer. Lastly, cost savings. Preventing corrosion through regular maintenance and protective measures is far less expensive than replacing damaged parts or dealing with the aftermath of a failure. Understanding the types of corrosion, their causes, and how to treat them is essential for anyone involved in the aviation industry. It allows for better prevention strategies, ensuring that aircraft remain safe, reliable, and efficient. Regular training and updates on corrosion control techniques can keep personnel well prepared. Corrosion in aircraft is a serious issue, but with proper knowledge and preventive measures, it can be managed effectively. That's all for today. Signing off, Group Buckshot.